Whenever I get a call from my students the day before an interview, I always feel helpless because can you imagine India, we have 1.4 billion people and getting a job is so important. Not only getting a job, but also you have to work throughout your life. Imagine your 40 years career. Statistical modeling is required. You work in data science, actual science, AI, in any field because the world is statistical presently. For the first time, if you are studying linear regression, you entered the world of statistical modeling. So when you enter the world of statistical modeling, if you don't understand the concepts properly, how can you use distribution here? What is the meaning of normally distributed data? All those I'll explain today. Then it will be very difficult for you. The day before interview, you can never prepare for the interview. It takes a lot of time. You can only develop in course of time. Suppose you are spending 2 hours a day. You make it 2 hours 15 minutes. That's all. Extra 15 minutes each day you need to spend towards developing concepts. If you study like mathematical equations, it's not going to help you. Ultimately, what will happen? If you think that you will develop later once clearing the exams, it will not happen. It takes time. So every day you need to spend some time. You are not going to Mars. Time and again I say you need to learn something extra, little bit 5% extra you need to give. Today I will discuss a very very important concept which will definitely help you not only clearing the exam, writing the paper. That's very important. That's where you prove your worth. Appearing the interview, you need to prove yourself once again. Not only that, while working also in the company, you need to prove each day. Now it's a crucial time if you are studying linear regression, and I've already given 3 classes. This will be the 4th class. In today's class, I will discuss a very, very important concept. Stay till the end. Definitely you learn something. Let's get started. Mostly in today's class, I'll spend 20 minutes discussing this one and 10 minutes the problem, what we are trying to solve in today's class. So if you go through this example, here, if you see, here we get the word mean, and here on a particular day, what we want to know exactly. A water utility company, they may want to estimate the mean daily water consumption for a given temperature. That is mean predicted response. How about the second one? They may want to predict water on a single day, daily water consumption. So you are finding the mean. So when you are finding the mean, you are predicting the mean. When you are finding on a single day, you are predicting the single day response. Remember the 2 words only here, nothing more than that. Day like this where you have 48 degree or maybe 45 degree, the consumption will be more. So on a particular day, if you are predicting, definitely that is not same as mean prediction. That you need to remember. So what we are actually studying in linear regression, that's what we need to learn. This is my graph, okay? We'll try to understand what is this graph. What is linear regression here? So what we actually do, if this is the regression line, we predict the mean. This is mean of normal distribution. This is our data. So everything you need to know. If you didn't know this by now, you will not understand here. Okay, I know that. So what we'll do is, through example, we'll try to understand. I'll come back to this once again. Now, this is one of the examples. This is the question. We'll see how to solve this question. Now, this says a university wishes to analyze the performance of its students on a particular degree course. It records the scores obtained by a sample of 1 to 12 students at entry to the course and the scores obtained in the final examinations by the same students. The result are as follows. That means if someone appears in entrance examination, this mark if you see 86 entrance examination, and also you have the data of the final one. When we say final one, that means after studying for 3 years, you got the result. So of course, you appeared the entrance examination and you got selected to study in that particular college. And remember, we got data like this. So what is data? When we talk about data, we make a mistake. And these are interview questions I'm saying. What is the meaning of data here? So when we say data here, what is the strength or length of data? You count, it's 12, it's not 24. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So data y1, y2, never forget about this. Even when you go to GLM, generalized linear models, you see the density function you will get always like this, fyi, not fxi. If you think xi is data, no, it's wrong. So please rectify, because many they ask me when I say data y1, y2, yn, they say what about x1, x2, xn? They are only a reference point. They are not data. Okay, 86 is a reference point. 53 is a reference point. 71 is a reference point, not data. Achha, that is the first one. So what we do in normal, when we study in linear regression, normally we predict a value for the future. How we predict? We predict this way. This is our tabular data. Okay. Suppose, let me write here, these are the students, they got admitted. You can enter 1 year. Suppose in 2022, they are passed out students. They got their result normally in the month of July. We have both the results, the entrance examination when they entered in 2022 and the final score when they got the marks. Okay, done. Now for the future, suppose now today we want to know someone joined in 2023 and that guy will appear the examination in 2026 April, and subsequently he or she will get the result in June, July. So we have 2 months time, right? So what we know? We don't know both. We know only one. We know the entrance examination. Now the question is, if someone comes here and says, could you say me something about my final result? We say definitely, because they know that we are doing some kind of statistical modeling. We'll be able to say something. If he comes and says, say something about future result, then you will say definitely, we are here to say you something. So you are ready to say something. How can you say? You say that in this kind of modeling, we need the independent variable, the covariate. That means if you say something about your entrance examination, if you appear the entrance test, we need to know that. If this guy says, yes, I appeared entrance examination and I got 60. Suppose this guy says I got 60. But remember, this 60 is not same as this 60, because this is another guy who already passed out in 2025. We are predicting for someone who is not this guy, who is another guy. It's another thing that marks the match. He might come up and say that I appeared the entrance examination and I scored 61 in entrance examination. Then it's a non-tabular point. It's not here. If it's 60, it's a tabular point. Doesn't matter. Whatever it is, we will not rely here. We will not definitely find from this line, the second line data. That is sample. So we'll use a sample, not for prediction. So if it's a tabular or non-tabular point, it doesn't matter. We want to predict. Now, before predicting here, remember the data is 12 here, n is 12. Let me write y1 to y12. This is our data. y1, y1 is 75. That way, this is your data. Data distribution is normal. That means what? That is what we'll try to know. Data distribution is normal. Also, let me tell you one thing. Make it very, very clear mind. You learn what is modeling. See, suppose someone appears the examination, today only appeared the examination just now, he's coming out of the room and you predict for him. I mean, we have a line, equation of the line. Let me write, this one I already covered. Y is equal to alpha plus beta x. This will be our linear line. I've given 3 classes. If you didn't do that, you can go and check. So for xbx, you will predict y. So if you know alpha and beta, I already wrote here. I will take those. See, I got 205. Done. So if you put x here, you will get y. It doesn't matter x is a tabular point or it's a non-tabular point. You put x, you get y. That's done. These are estimated values. Done. But now the real understanding starts before predicting. So let me erase this one and we'll focus on the distribution part. See, actually what we are doing. That's what we'll try to learn. Let me erase all. Yeah, we'll clean it. Let's not be in a hurry. So if you check here, In future, suppose someone appears on examination and he got 60, a new student, not this student who already passed out. We don't need to predict for this guy. That's a random variable. That's not a constant. See, what is linear regression? What we are actually studying for 60, for the value of 60, in future you are predicting, suppose someone just appeared in examination, he came out, and we asked him the entrance exam score, he says 60. For him, we are predicting, first of all, we will say, will not be able to say something, because how can we say? God knows, we don't know, right? That should be the answer. So we have no idea absolutely, right? It's a random variable. As a statistician, we have to say something. So we'll write the name of the random variable. What is the name of the random variable? We will say, first of all, even if, even if we don't say, we know that this random variable is y4. This random, the name of the random variable is y4. I have written data, see here. Let me write properly. This is y4. I've written the data small y4. So this is my random variable. And when I collected data in linear regression, that means I collected one point. See, I got only 1 point. I'm supposed to collect lot of data, probably 1,000 students I might ask to say something, but I asked only one. On the basis of one, can I say something? Yes, definitely. We find that a confidence interval, but you are supposed to take a lot, but with one sample we do. We test a hypothesis. Similarly, here we take for each random variable one data. This is one data for this random variable. How about this? This is also one data. This is also one data, 74, one data for random variable y3 corresponding to x3. x3 is reference. So if the reference is 71, it's not data. 71 is not data. That is reference in linear regression, remember. So if you are predicting for someone who is 71, this is y3. This is a random variable. So we collected one data for y3. Okay, what are the data? 74 years, 68 years, 70 years, 75 years. For one random variable, one data. Now, in this graph, you see, I will show what we are saying here. Suppose this is the first one, or I mean, you write according to increasing order. Okay, whatever it is, this is 1 point. This is 1 point, right? This is 1 point. This is your x1. Okay, this is your x2. This is your x3. This is your x4. This is your x5. This is your x6. This is the true, let me write true regression line. We try to fit it, that's a separate thing, but suppose this is true regression line. This is my true regression line. Okay. If this is my true regression line, we try to fit with the data and try to reach with this, then we check the residuals, all that will come later. But this is my x1. For this x1 value, what are the values I have? I have so many values. It could be this one, 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 it could be this one. So what is my sample? I got a sample somewhere here. My sample falls here. It passes through mean, that's a separate thing. Where is my sample? Y1. What is Y1 for X1? So my sample is, suppose here. Suppose my sample is this one. Fine, no problem. No, not this one. From here we'll take. So we'll take this. Okay. Now suppose my sample is this. Sorry. My sample is this. My sample is this here. Okay. And in the second case, my sample is here. In the third case, my sample is here. Because there is an error, right? We are not taking the line through all the points. It's not curve fitting like mathematics. We are finding the line of best fit. I explained already what is the line of best fit. If you didn't watch, you can go and watch. These are my points. These are my points. And see, these are my points. Like this, 1, 2, 3, 4, 5, 6, whatever. And my line is this. But again, you need to understand what is the meaning of this normal distribution. That's what I'm saying. There where you will get mean predicted response and individual predicted response. So what we actually do, okay? We observe one sample, this is y1 for x1. So of course there is error, this is e1, we say this error, okay? And this is the error here, this is the error here, these are the mean values, this is the error, this is the error, e1, e2, whatever you write, residuals, errors, okay? And this is our line of best fit. Technically it should be the true line, but this is a sample regression line, okay? From the sample data, we try to reach to our true line. So now this is our true line we try to reach, okay? Anyway, this is our fitted if you consider. So what will happen is, this is our error. So what is data distribution now? Because there are a lot of options for you. It could be here, it could be here, it could be here, where a random variable comes. If you ask me when will be your next class, I can say you join anytime I take. So that's random pooling. But if I say I can take only Monday, Wednesday, Friday options, there comes your randomness, right? Here, there are so many options. Like I explained, if someone gets entrance examination 60, there might be so many students, right? So that's where option comes. But here you have highest probability. That's where it follows a normal distribution. Again, this is assumption. Let me write the assumption here. What is the assumption? Now here, y1 follows normal distribution. Y1 follows a normal distribution. What we predict also, I'll let you know in 1 minute. Y1 follows normal distribution with mean. I showed you this mean. This mean. This is the mean. This is the mean value. This is the mean. Again, when we say normal distribution, we are not talking about one random variable here. We are talking about n number of random variables. So y1 is a random variable and it follows alpha plus beta x1. This is the mean. I showed you already the mean here. This is alpha plus beta x1 corresponding to x1. And sigma square. Sigma square is constant. That's a part of assumption here in linear regression. Okay. So our assumption is this is normal distribution centered at alpha plus beta x1 sigma square. If you see second one also, from point to point, only the mean changes. Here mean will change alpha plus beta x2 and sigma square. That way my nth random variable, if someone will ask you how many random variables you are studying in linear regression, you don't say x and y2. You say y1, y2, yn corresponding to x1, x2, xn. Okay. So these are my random variables we are studying. See, if you don't know this, how can you find a confidence interval? How can you test hypothesis? I mean, everywhere you need distribution. Without distribution, see, after studying distribution, then only confidence interval comes. Hypothesis test comes. How can you test for that? Whatever hypothesis test you are doing here. Okay. So again, here let me take this opportunity to say you something more that is required here also. What is that? Remember, our modeling is actually y is alpha plus beta x plus c. If E is not there, then what will happen? Your model will directly change to a mathematical model. Mathematical model means you are predicting everything. Everything is deterministic, mathematical. It's exact. It's not different at different times. Suppose you are predicting something for 2028. Can you bring everything into your model, like the weather, the government, the crop production, everything? No, there will be some random variation. Even when I say I give a class for 1 hour, I don't give exactly 1 hour. Sometimes 58 minutes, 1 hour, 1 minute. And that 58 minutes when I give a class, 2 minutes, I don't give or 1 minute. That was not planned before. On that day, suppose I'm giving a class now. Today there were some disturbances, right? Before. I didn't know about that. So whatever thing you can predict before, that will go into E. The Katrinas, the natural calamities, the tornado, the hurricane, the drought, whatever all you see, those will be under E. But yeah, if E will be very high, then there will be problem. Company will go bankrupt. Okay. Anyway, I'm not going to that. This is the deterministic part of the model. And this is the indeterministic part, which is not under our control. Okay. But we'll try we try that seeing the sample, the errors are minimized here. Sum of square errors in LSC, but here we are using the distribution. Okay. Now, E is stochastic. So what is the assumption of this normal distribution? This is one assumption. So all remember, sigma square are same. That's why all the normal distribution, they look alike because the variance is not changing. If the variance will change, then what will happen? One will be a smaller one will be a bigger one, but all are same. They are looking same. Means what? Their variances remain constant. This is a property. This is called homoscedasticity. When you go to CS2, you will study time series. There you will come across the other one also, heteroscedasticity. Homoscedasticity means what? They are the same. Variance is not changing. Again, variance is not changing means what? There is a meaning. Okay. E1, E2, EN. These are, I mean, if I write this way, let me write Y1 is equal to alpha plus beta x1 plus E1. What is Y2? Alpha plus beta x2 plus E2. What is Yn? Alpha plus beta xn plus En. This is my distribution of data. Now, what are E1, E2, En? They are, no, because the error here comes from the error part. When you go to GLM, what is the data in GLM? Exponential family. Whatever you have in exponential family, that is the distribution of data. Here, what is the distribution of data? Normal. They are whatever is in exponential family in GLM, like your gamma distribution, binomial distribution, exponential distribution, Poisson distribution, all distributions we consider in GLM. Why? There is reason. I'm not going to that now. But here only normal distribution. So the distribution here in linear regression comes from their errors actually, from error distribution, because you are just adding this deterministic part. This is deterministic part. So error distribution here, error follows normal distribution with mean zero. There is a meaning once again, and variance constant across. Okay, like everywhere sigma square, sigma. It's not sigma 1 square, sigma 2 square like that. So what is the meaning of this error mean zero? Error mean zero means what? Means suppose I say you to give 1 hour class each day. Sometimes I will give 58 minutes, sometimes 1 hour 2 minutes, sometimes 59 minutes, sometimes 1 hour 3 minutes. That way what will happen is sometimes little bit positive, sometimes little bit negative. You will not mind. However, suppose each time I give you 58 minutes or 57 minutes class, one day definitely you will say, sir, why not make it 57 or 55 minutes, whatever you're taking that time. You change your class timing. Because I mean, there is a pattern now that every time I'm taking less, it's not random. Whatever is random, that will be in E. Okay. And here we assume that sometimes positive, sometimes negative, they will cancel out. Okay. That's where E follows normal distribution, mean zero. Mean zero means what? Sometimes +1, -1, +2, -2. That way it should be zero. Okay. And variance sigma square, variance should remain constant. And we try to contain the variance. Constant means what? They should not change from point to point. Okay. So that means suppose I'm giving a class on an average, I vary 5 minutes. That should remain constant for every class. Today, suppose I gave you 58 minutes class. Tomorrow, 1 hour, 50 minutes class. There is a lot of variation, right? Variation changes. That's a problem, right? So it should be constant. Anyway, now come to this one. So all are normal. See, this is my random variable for x1, my random variable y1, because there are so many options. We got one sample after those. Okay. And the distribution is the maximum probability is here. That's where mode comes here for normal distribution. Mode, mean, median, they all fall here, right? So alpha plus beta x1 is what you get from the equation of the line. And this is this point. This point is your alpha plus beta x1. This point is alpha plus beta x1 part. This point. Okay, let me use another ink. This point is your alpha plus beta x1. This point is alpha plus beta x2. Similarly, this point is alpha plus beta xn. Okay, so the means are changing from point to point. Mean of what? Mean of y. So what we are modeling? We are modeling mean. What we are predicting in linear regression? Mean. How? I'll let you know. What actually we are doing. You will understand fully. So what actually we are doing in linear regression, we actually predict the mean. Again, I will repeat. We actually predict the mean E of y, alpha cap, beta cap x. Okay. So what we predict is for a given value of x. If you really want to write, so you have to write so much. Okay. Why actually this is y given x. This is the correct one. Okay. Even this is not the correct one. The correct one is this. For a given value of x, x0, x1, x2, whatever. But I mean, we don't write all this. Just remember here, expected is 0 because we have assumed this one. Okay. These assumptions also we need to verify. Okay. That is post analysis. Once you apply the model, E of is 0. So if you take E of y, that is this for a value of x. Okay. Whatever value x1, it could be x1, x2, xn. So for this one, what we do normally write is, for this one, normally we write, we should have written mu is equal to, again, because this is the mean, what we are predicting, I'll tell you once again, but we are writing here y, which is, I mean, ultimately we'll do that, but that's not correct. So this should be mu actually, because you are predicting mean value. So this is what we predict ey. This is what we predict, means what we predict. See, we predict this. Suppose at this point you want to predict, at this point you want to predict. Let me use this from here. And suppose you want to predict here. Let me use another one, this one. You want to predict here, or maybe red one, so that you will be able to see. Suppose you want to predict here. Oh no, I'm not happy. Here, okay, here you want to predict. What you are predicting that on this line, right? On this line, again, a normal distribution is there. You are predicting the mean here. This point is the mean of the normal distribution at that point. So what you are predicting, the mean value. Okay, you are predicting the mean value. Try to remember, even if you don't understand, it will be worth knowing, because with time you will know if you don't know now, right? So you are predicting the mean. This is mean predicted response, nothing new to learn. Whatever you are doing, mean. But for practical purposes, what we do is we write for the same one y. So when we write y, what we are assuming, this is individual predict, I mean, individual predicted response. Suppose I say that the mean pass marks for the students who will appear CS1 exam from Institute and Faculty of Actuaries will be 58. Okay. But probably for this year, that might not work, right? So when you make it personal, it will be different, right? Suppose in your class, the mean mark is 58, or whether mean temperature you find, but on a particular day, it might be different. Okay. The water consumption I said, or the electricity consumption. Suppose today is the final cricket match. Okay. So definitely there will be more electricity consumption. So individual, when you say, that is different from mean. That's the difference. So yes, so we are predicting, this is mean predicted response. Already whatever we are doing, that is mean predicted response. So we'll try to understand what is individual predicted response, what we don't do normally. That's what we'll try to learn. This is alpha plus beta x. We write for any value of x. Suppose x value, you take x1, x2, whatever value we put, you get this one. Okay. So here, because we don't know future error, we take 0. Okay. But remember the difference. Why that? Even there is a graph, I didn't bring that one because it will make you more complicated. Okay. So here, this is not exact. Let me tell you. Here, we are ignoring E. Okay. And then we are saying y cap because we don't have idea about the future error. We say y is also alpha plus beta x, but still there is a difference. Why there is a difference? The variants are not the same. Variants are different. There might be a lot of variance when we talk about individual one. When we talk about collective one, there is a little variance. Suppose your class, you find the mean weight. Okay, mean weight if you find for the same cohort every year, there will be a little bit difference. Okay, but if you find individual weight, there will be a lot of difference because individual weight, suppose someone is 55 now, probably next year he will be 65. There will be 10 kilo difference. But mean suppose 55, it will be 56 because someone will grow healthy or fat, whatever you say. Someone will also, I mean, there will be opposite effect also, right? So what will happen is they will average out. Someone will also reduce weight, right? So that way, if you compare averages, that's different from when you compare individual. So that's what we'll do here. This is the question. What is the question here? I'll show you the question now. When we talk about mean of everyone, that's mean daily water consumption. When you talk about a single day, that will be different. Okay. So when you predict mean, it's like going back to this, how it will be. Let me explain. In our example, what we predict actually, let me tell you, what we actually predict is, okay, here also two questions. You should be very, very clear. Two kind of questions. This is going to be very, very important when you are studying modeling parts. Now, what is that you want to know? Two things you need to know here that will help you going ahead. The first one is, suppose we have a desk here and we claim that we have a model ready and we'll predict. Okay. You have a table, everything is here, and you have a calculator, whatever. And someone comes from the exam hall. You are saying him, would you like to know the mark? Definitely you will say, yeah, definitely I would like to know because the result will come after 2 months. So say something about me. You ask, did you appear in an entrance examination before entering this college? He will say yes. Then you ask that mark. Suppose he says 61. This is the entrance exam score. This line, okay, 61. Then you put 61 here in that equation. So we'll write y is equal to alpha plus beta x. And we have already estimated alpha and beta by now using the past sample, this sample. Now put here, because we estimated alpha and beta, and this is mu actually. That's what I'm saying. How mu and y will differ. This is actually mu. Okay. We are predicting mu for him. Okay. Mu for him means, that means will not change. We'll say the same thing for everyone. Okay. That means, what is the meaning of that? Suppose another guy comes. Another guy. This is A, this is B. For A also will predict. Suppose you put 61 here, alpha, beta estimated value and x value you write here, 61. Then you predict. Suppose the mark you got 69. What we are saying is, we'll predict 69 for all the guys who got 60 marks in entrance examination. We are not changing. It's not individual prediction. We are predicting the average for everyone. Again, there might be a confusion. Average means not average of these. That's another confusion. Number 3 confusion. See, when I talk about average, no. Because in linear regression, we are not predicting that way. We are predicting what? For a given value of x, we are predicting y. That means if you have chosen 71, you forget all other things. Okay? Or whatever I said, 61. So I'm talking about all those students. Suppose out of 1,000 students, 10 students said we scored 16 entrance examination. I'm talking about those 10 students and I'm predicting 61. I'm predicting the mean. For everyone, I will say 69. Irrespective of their preparation, 3-year preparation, irrespective of any other factor, we'll predict 61, but that's not true. That's not true. How that's not true? Suppose out of these all 10 students, suppose someone is not well, very, very unwell. Okay. If someone is very, very unwell, what will happen is, this guy, suppose B is very, very unwell. He entered the examination. He didn't write anything at all. He came outside. So when you predicted 69 for him, he might say, you know what, I didn't write anything. I just, I was sitting writing question paper all that passing time because I dysentery. I was not feeling well throughout the exam. So how you are predicting for me 69? What answer you will give? What answer you will give? First of all, the first is, let me write here, you have to say, okay, no problem, because our model didn't work for you because we consider only entrance examination. We didn't consider any other factor. Okay. So if every other factor remains the same, like you appeared the examination properly, you are well throughout 3 years, your faculty they taught well, you also spend time properly, all other factors. Otherwise, you go on increasing covariates, x1, x2, x3, like that. Now in this model, we made it very simple. We consider only one covariate, only one independent variable. You can say to that guy, okay, but you are not unwell, so that whatever you are saying, that's not captured in our model. That's what you can say. Okay, that's what. That's one. So when you are predicting individually, you are predicting an individual in that case. So, but in normal, I mean, in linear regression, we don't do that. We always predict mean. Okay, remember, not individual. We always predict mean. So individual variance could be different. See, this is the formula. I mean, this I already taught SXX, SYY, SXY. Okay, you find alpha, you find beta. Okay, I've written here because I want to find. See, this is what we'll use the distribution. Without distribution, you can find confidence interval and you can test per hypothesis. Here also the population is normal. Okay, a t distribution we are using because you know when we use t distribution, right? This is regarding the variance. So when you solve this kind of a problem, so someone got 53. You find a confidence interval for the individual predicted response and for the mean predicted response. So this is given. You don't need the proof. This is for individual, little bit high. That's why you see 1 here. And there is no 1 here. Okay. Now how you do the problem using this? I mean, we don't need to know anything when we are finding confidence interval. Okay. So what we do is, if you are finding a confidence interval 95%, suppose 95 will write, we'll keep margin 2.5% both the sides. Here this T10 will write 95%, means both sides margin will keep 2.5%, and we'll see the table. This is our T10 distribution. Okay, we'll see the table. We'll keep margin 2.5%, here 95%. So the values we'll get from here, I think 2.888 probably. You see 10 here, 10, 2.228 here, 2.228, 2.5%, 2.228, 10 degree of freedom. So 2.228, it's symmetrical. And you know the distribution here, this for mean predicted response for individual, you have to use this one. So I'll use, see, even if I change mu0 here, that will not make a difference because minus a is there. If you multiply minus here, this will come this side, this will come this side. If I change this two, so because it's like minus a, there won't be any problem. Now this part, everything I'm writing here, square root of all that, I mean everything we know here. N we know 12, we know x naught 53 given. For this value we are predicting 53, and x bar, you know, the mean of x values divided by SXX, you must have found. You put everything here, sigma square, put everything here. So we take the estimation here, put everything here, and then cross multiply. Okay, you take this side, this side. So what will happen? You will get probability. Then what will happen? Mu naught minus mu1 you will get. Suppose you will get A and B here, these values. Then you find for mu naught. Mu naught will be equal to probability A plus mu1 cap, then B plus mu1 cap. That's all. Okay, that way. So this is what the solution is. Here you can check. This is the solution, direct solution. Yeah, this is the direct solution because this is the denominator part. You find here this denominator, and this denominator I multiply with 53, then add this one. This is mu naught cap. Okay, mu naught cap means what? The mean prediction value, okay, for the value of y. And this is our confidence interval. Okay, what is the meaning of this? That's another question. This is confidence interval, means 95% confidence interval. That means the mean prediction mu for what? For x naught 53. So you write always here for 53, because if you change, your mu will change. We say mu will be between this 56.2, 67.2 with 95% confidence, means it's not the probability, because either it will be here or it will not be here. If you ask me, the mean here, mean lies between this. That doesn't mean that there is a 95% probability. This is also wrong interpretation, but that I covered in confidence interval. This means actually, because it will be either here or not here, the mean, we don't know the mean, right? That's why we are finding a confidence interval. The mean will be in this interval or not. So if you do it for 100 times, in 95 cases, mean will be here. That's what you can remember. So this is mean predicted response. So when we talk about individual predicted response, if you see here, this one changes, but how we predict individually? Let me go to the diagram. So the individual prediction, it could be anywhere on the line. Okay, individually we are not doing the mean. So what will happen is there will be a difference. Okay, but future error, we don't know. We take 0 and we normally write this. It's an estimate. Mu is equal to mu cap is y cap. Okay, but there is a means are the same. I mean, whatever is the mean here, mean y, we take that as y. That's all. Okay, because we don't have any idea. If you ask me where that variable comes, suppose for example, state of Hormuz, from there we get the like the ships they are coming, right? That's why there is LPG problem now. So if you find the mean time it reaches India, I mean today 26 it was supposed to reach the ship, I forget the name, but this time if you ask, this is individual, it will be different from the mean time because there is a war situation. So that's where it's different from the mean one. Mean there is a mean time when it starts from here, what time it reaches, but this time might be different, right? But this kind of a random error, it was not known before 6 months when it must have modeled. I mean, when it was modeled before, right? So that way you can interpret all the time. That's all for today's class.